Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. In Unit 4, we are studying about Heterocycles Part 2. In Lecture 4, we will be studying about Pyridines, synthesis, reactions and applications. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project was sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered in this session include synthesis of pyridines. We will be studying about the Hans pyridine synthesis, Guerci synthesis, Boltzmann-Rath synthesis, Chichibabin pyridine synthesis, Gattermann-Skitta synthesis, Siamisen-Denstadt rearrangement. And afterwards, we will be studying about the reactions of pyridines. We will be studying first about Menstrukin reaction, electrophilic and nucleophilic reactions of pyridines, oscillation, reactions with organometallics, and free radical reactions and cyclizations. Welcome to the next session on the Heterocycles 2. Now we are going to look at pyridine and its derivatives. So pyridine actually belongs to 6-membered rings. So here now we will be studying about heterocycles with 6-membered rings. Pyridine, quinoline and isoquinoline are some of the examples. The structures are shown here. Pyridine is having a 6-membered ring with one heteroatom, that is nitrogen. Quinoline and isoquinoline are having 2 6-membered rings, and the position of nitrogen is only changed. Both of them are having only one nitrogen. Indole is an example of benzopyrrole. Here we have a 5-membered heterocycle, that is a pyrrole type heterocycle is shown here. It is also having one nitrogen. The pyridine was first isolated from the bone oil and was highly stable. It undergoes substitution rather than addition reactions. So these are some of the examples of heterocycle, 6-membered heterocycles we will be studying in this particular session. Some important pyridine derivatives are shown here. Nicotine, which is present in tobacco, has a pyridine ring. Sulfapyridine is an antibacterial agent. Pyridoxine is an important cofactor. It's vitamin B6. And quinine is a poisonous principle in hemlock. This is a toxin. So pyridine actually does both the good and bad properties. Let us look at the resonance in pyridine. The pyridine can be represented in various resonance forms. They are shown here. The first two forms are basically the Kekulé forms, that is how we represent benzene. The same way here both the pyridine are shown in the Kekulé form. These two are non-charged or uncharged pyridine rings. And we have 3 other forms which are having a charge, that is nitrogen is having a negative charge and the carbon is having a plus charge, and these are all the various resonance forms which represents pyridine. Dipole moments of pyridine is 2.3 dB and piperidine is 1.2 dB, which shows that nitrogen atom in the pyridine carries a greater negative charge compared to the fully reduced piperidine moiety. And all atoms in the pyridine are in the sp2 hybridized state, and each atom has one electron in the p orbital. They form the pi aromatic sextet, that is 6 electron is formed from this pi ring is formed from these 6 electrons, and the nitrogen is having a lone pair of electron which is perpendicular to the plane. So this is the reason this nitrogen's lone pair is not involved in the pi bonding, so that makes the nitrogen more basic, because this is available to act like a base. Let us look at various synthesis of pyridines. We have CC bond formation, under which we will be looking at the Hans pyridine synthesis. We will have some acyclic precursors from which pyridine can be synthesized. From dicarbonyl compounds also we can make pyridines and ring expansion. These are all some of the reactions we will be studying about for the pyridine synthesis. Let us start with the Hans pyridine synthesis. So here an aldehyde and dicarbonyl compounds are involved in the condensation reaction. So here two molecules of a 1,3-dicarbonyl compound and benzaldehyde, any aldehyde in this particular case, we are talking about benzaldehyde, are condensed in the presence of ammonia at a pH 8.5, that is under basic conditions. So these undergo aldol condensation and dehydration. So this is the first step. So this intermediate is formed, which again further undergoes Michael addition with the 1,3-dicarbonyl compound to give this intermediate, which can undergo displacement of one of the carbonyl oxygen by the amino group, that is the ammonia, which we are using as a base, is the one which is incorporated here for the nitrogen ring formation. So these kind of reactions you are already familiar with. Lone pair of electron on the nitrogen attacks the electrophilic carbon and the bond is polarized towards oxygen, which leads to the cyclization. So this is what is generally the dihydropyridine. So the actual Hans pyridine synthesis stops here as the dihydropyridine stage. This is taken and further oxidized using a strong oxidizing agent to the corresponding pyridine derivative. So this is the final step we have to do separately to convert the dihydropyridine, which is formed from the Hans pyridine synthesis, to final pyridine derivatives. Here we have a completely substituted pyridine derivative that is formed. And let us look at synthesis from 1,5-dicarbonyl compounds and ammonia. So here 1,5-dicarbonyl compounds are taken, and when they are treated with ammonia, this actually gives a cyclized product. Of course, there are various steps involved in this one. In the beginning stages, this particular carbonyl oxygen is replaced by the ammonia group, that means NH2 is replaced here, and this undergoes the cyclization as we had seen in the previous one, and that cyclization leads to the dihydropyridine derivative, and this on further oxidation leads to the pyridine derivative as shown here. Here again we can have multiple substitutions on the pyridine ring. We also have another reaction in which a ketone, an amino ketone, is reacted with the cyclic carbonyl compound, that is cyclopentanone, at 170 degree. So this reaction gives a condensed product, and this on treatment with ammonia and ethanol gives the dihydropyridine derivative, which is further oxidized to the final pyridine derivative as shown here. The same can also be effected by treatment with hydroxylamine. So this 1,5-dicarbonyl, if you look at here, we are starting from 1, 2, 3, 4, 5. So this again is a 1,5-dicarbonyl compound which is treated with the hydroxylamine, produces the same cyclized product as shown in the previous one, and this is having the N-hydroxide derivative, and this on this dihydropyridine derivative can be converted to the pyridine derivative after dehydration. So these are a couple of reactions by which we can actually prepare the pyridine derivatives. Then we have the Guericke synthesis. In this one, 3 amino acrylates and enol ether of 1,3-dicarbonyl carbonyl compounds undergo condensation in the presence of a base like a potassium carbonate in a solvent like acetone. This leads to the condensation and the cyclization to give the pyridine derivative. Cyanoacetamides and 1,3-dicarbonyl compounds can also undergo condensation as shown here. This is actually the pyridoxone unit, which can undergo resonance tautomerization basically to give the pyridine derivative. So here we will be having the hydroxide derivative, and this hydrogen from the nitrogen shifts to the oxygen. So we get the 2-hydroxy derivative. Then another synthesis is treatment of 1,3-dicarbonyl compounds with 3 amino enones. This also undergo condensation reaction to give the corresponding cyclized pyridine derivatives. Boltzmann rod synthesis. In this particular reaction, the condensation of an enamine, so this is the enamine, and ethenyl ketones. So basically the E group is a electron withdrawing group generally employed in these kind of reactions. So when these two are treated at 50 degrees centigrade in ethanol as a solvent, they undergo the condensation, and then finally this final cyclization you are already familiar with. So this nitrogen lone pair attacks this electrophilic carbonyl carbon, which undergoes cyclization to give the corresponding pyridine derivative. So this actually occurs at a very high temperature, that is 150 degrees centigrade. So basically the condensation of the enamines with ethenyl ketones, that is alkyne ketones, leads to an aminodiene derivative. This undergoes E is that isomerization on heating, followed by cyclodehydration to give the 2,3,6 trisubstituted pyridine derivative. Formation of two pyridones, as I have mentioned in the earlier also. So the two pyridones are basically hydroxypyridines, so they can exist in the resonance forms. So this two pyridones can be formed by the condensation of enamines with 1,3-dielectrophiles. So this is another reaction where pyridine can also be synthesized. From oxazoles also we can synthesize pyridines. So the oxazole basically undergoes reaction very similar to undergoes Diels-Alder reaction basically. Then retro-Diels-Alder reaction rearranges the compound into the corresponding pyridine derivative. So here we have the oxazole reacting with the dienophile, that is acrylic acid, to give pyridines after the rearrangement of this formed Diels-Alder adduct. Then the next one is the Chichibabin pyridine synthesis. So here the condensation of aldehydes, ketones, or alpha beta unsaturated carbonyl compounds, or any combination of the above in ammonia or ammonia derivatives. So this is the, here we have shown ammonia directly, and the sodamide is used as a strong base for this particular reaction. Any other ammonia derivative can also be used in this particular reaction. So this condensation leads to the formation of pyridine derivatives. And the Gattermann-Skitta synthesis is shown here. Here, the sodium salt of malonic ester is treated with dichloromethylamine, and these two undergo condensation reaction to give pyridine derivatives as shown here. This is also another method for the synthesis of pyridines. Then Siamisen-Denstadt rearrangement. This is basically the ring enlargement or ring expansion reaction. So this reaction is basically similar to the generation of the dichlorocarbene, because chloroform and sodium hydroxide treatment generally gives the dichlorocarbene. So the formation of the dichlorocarbene adds to this particular double bond to give a cyclopropyl derivative, that is the dichloro derivative. And this cyclopropyl dichloro derivative undergoes ring expansion with the loss of hydrochloric HCl to produce the ring expanded pyridine derivative. So this is basically the ring expansion reaction. So here, as it is mentioned here, the heating of chloroform or other halogeno compounds in alkaline solution leads to cyclopropane intermediate, that is the dichlorocarbene is produced, which adds to the pyrrole to give the dihalogenocyclopropane, which is quite unstable and which actually undergoes ring expansion to give the 3-halopyridine derivatives. Then let us look at reactions of pyridine. So in the reactivity, we are actually compared to the corresponding benzenoid compounds. These are basically electron deficient. The electron deficiency arises because of the electron withdrawing nature, that is the inductive and the mesomeric effect of nitrogen atom, because there is nitrogen atom present here. So due to which it is actually an electron negative atom, so it pulls the electron towards itself. That makes the aromatic ring electron deficient. So if you look at benzene derivative, the electron density available is 1 for all the carbons, whereas in this particular case there is less than 1 electron density available. That is because the nitrogen is pulling more electron towards itself. So these M effects are more pronounced at C2 and C4 carbon. So that means this C2 carbon is more electron deficient. The C4 is the highest electron deficient one with the 0.951. Whereas the third carbon, this is 1, 2, 3, 4. So the 4 position and the 2 position are more electron deficient, whereas 3 position is comparatively electron rich. This is responsible for the varied reactivity what we see for pyridine derivative, and pyridinium cation is also shown here. Pyridine being basic can actually abstract a proton and form the pyridinium cation. Menstrukin reaction is shown here. This is basically the quaternization of pyridine with the alkyl halide or related compound. When an alkyl halide is treated with the pyridine, we get the quaternary salt as shown here. So this is the Menstrukin reaction. So here the nitrogen is having a positive charge. Let us look at the acylation reactions of pyridine. So acylation of pyridine can be achieved as low as minus 78 degrees centigrade. So the pyridine can be treated with acid chlorides or anhydrides or sulfoxides or thionyl chloride, leads to various acylated or sulfonylated products. And acyl halides and basically the chloroformates reacts instantaneously with the pyridine to form the corresponding pyridinium salts. So this chloroformate reacts with the pyridine. In all the cases, if you look at the reaction occurs on the nitrogen only. So the acylation actually happens on the nitrogen atom only. And pyridine also reacts with sulfonyl chloride and anhydrides to give the corresponding pyridinium salt as well. So this sulfonated derivative is formed by the reaction of the sulfonyl chlorides with pyridine. Thionyl chloride also adds to the pyridine derivative to give the sulfonylated product. Let us look at the next reaction, which is the electrophilic reaction. So the electron withdrawing nature of the nitrogen in the pyridine actually makes that the heterocycles less reactive than benzene towards the electrophiles. In other words, the electron density is already deficient on this particular ring. So that means an electrophile which is actually having a positive charge cannot attack the pyridine ring, because the pyridine ring itself is having less electron density compared to benzene. So that is the reason, even though the electrophilic reaction does take place on this one, but under harsh conditions the reaction actually occurs. And this electron deficiency is profound at the 2 and 4 position that we had seen earlier. So the electron density difference is very crucial for the electrophilic substitution reaction. And the 3 position has a maximum amount of electron density compared to 2 and 4 positions. In other words, this clearly tells that the 3 position is more prone to electrophilic attack compared to 2 and 4 position. So that is what shown here. We have a 3 substituted pyridine derivative is formed after the electrophilic attack. And if it is a proton which is adding, which is the electrophile in this particular case, it does not add to the 3 carbon, but it adds to the pyridine nitrogen itself. So this is the pyridinium cation which we saw in the previous one, is formed when the electrophile is a proton. Let us look at the halogenation reaction. So the electrophilic halogenation of pyridine follows 3 undergoes reaction very fast, followed by 4, followed by 2. And pyridine, if it has some electron donating substituents, then the electrophilic attack takes place very readily. That means chlorination can occur at position ortho and para to the substituents. So those examples are given here. So here we have the pyridine, unsubstituted pyridine. So this on vapor phase only undergoes chlorination, that is the electrophilic halogenation takes place. This trichloro derivative is formed in only 9%, whereas the tetrachloro derivative is formed in 73%. So this reaction happens at the high temperature, that is at the vapor phase. When we have the hydroxy derivative, which is actually electron donating substituents, which is present in the pyridine ring, which actually facilitates the substitution reaction very effectively. So the electrophilic substitution basically occurs ortho to the hydroxyl group. So that is what it is shown here. We get a ortho hydroxy derivative to the maximum extent. So the other chlorination also takes place, but they take place because this is a para substitution. This again is a para ortho and para substitution. So only ortho product is formed, that is ortho to the hydroxy group is formed in major quantity, followed by ortho and para, then finally less amount of the only para derivative, that is the chlorine substitution takes place. And here we are looking at some of the bromination reactions. So the para-ethyl pyridine can be treated with the bromine and 65% oleum to give the ortho derivative, that is ortho to the ethyl group is formed in 81%, that is the 3 substitution takes place. The bromination takes place at 3 position, and 3 and 5 position, that is the disubstitution is formed in 7% only. And if we take just pyridine, treatment of pyridine with bromine and indium chloride at 100 degrees centigrade gives the dibromo derivative in larger quantity like 43%, and the monobromo derivative is formed in 21%. On the other hand, if we have a electron donating hydroxy group on the pyridine ring, so in this particular case we have various products. One is the ortho product. This is the ortho para substituted product. This is diortho derivative. So all the 3 types of bromination takes place when there is a electron donating group on the pyridine ring. The electron deficient group, the electron deficient nature of the pyridine actually makes the nitration reactions very difficult. Even the electron donating substituents like methyl hydroxy or NH2 increases the reactivity of pyridine towards nitrogen, but it is not very similar to how benzene derivatives undergo nitration. So the substituted benzene derivatives undergo nitration much better compared to substituted pyridine derivatives. Next, let us look at the nucleophilic attack at the carbon atom. So the nucleophilic chlorination of pyridine occurs basically at 2, 4 and 6 positions by the reaction of basically the pyridone, that is the hydroxide derivative, and when treated with pyridones with POCl3 or SOCl2 gives the 2 halo derivative. The nucleophilic substitution occurs at the 2 position. The hydroxy group here is replaced by the halogen derivative, and when the same is present at the 4 position, we get the 4 halo derivative as shown here. So these are some of the examples of nucleophilic attack at the carbon atom in the pyridine moiety. Acetyl hypochlorite converts pyridine into 2-chloropyridine as the main product, and 2-acetoxypyridine also is formed as a minor product because this is the reaction shown here. So this 2-chloro derivative is formed as the major derivative, and displacement of the O-acetyl group also takes place in this particular case as a minor product. The next, let us look at the reactions with organometallics. Pyridine reacts with organometallic reagents both as a free base and as a pyridinium salt. So normally this reaction occurs at the alpha position, but in certain cases it can be selective at the gamma position as well. And the reactivity can be enhanced by the presence of electron withdrawing groups. Ethyl magnesium or ethyl lithium when reacted with pyridine to give only the 2 substituted product. But a mixture of diethyl magnesium and ethyl lithium gives a mixture of 2 and 4 substituted product. So the reactions are shown here, like this is the pyridine derivative. Diethyl magnesium and ethyl lithium, when we are using it as a mixture, gives the 2 and 4 substituted ethyl derivatives as the product. If we use either diethyl magnesium or ethyl lithium as the reagent, it selectively gives the two ethyl substituted pyridine derivatives. So this way we can actually selectively prepare different types of compound. Then let us look at the heteroatom nucleophiles. Under normal conditions, pyridine generally does not undergo reactions with the nucleophiles, basically hydroxide group, but at high temperature the reaction occurs. Electron withdrawing substituents on the pyridine actually facilitate the reaction with the oxygen nucleophile. Displacement of nitrocyano and halogen can be easily achieved using oxygen nucleophiles. Then finally, we will look at free radical attack at the carbon atom. So here the radical reaction usually happens at the 2 position of pyridine. So in the presence of light, the reaction actually occurs, the free radical reaction occurs as shown here. When the R groups are ethyl, N-butyl, tertiary butyl or cyclohexyl, we have different yields of the product, and when we compare the 2 to 4 ratio, the cyclohexyl derivative gives the maximum 2 to 4 ratio of 3.1, and the tertiary butyl gives the minimum of 1.4. So that means both the products are formed under photochemical conditions. Another reaction is the cyclization reaction. So N-iodoalkyl pyridinium salts, as shown here, undergo intramolecular radical cyclization upon treatment with tributyl tin hydride and AABN to give the cyclized, fused, corresponding cyclized product is formed. So this is another reaction where we can form a fused ring using free radical cyclization. Let us recap what we have studied so far. We have studied about the various syntheses of pyridines. Mainly we studied about the Hans pyridine synthesis and Guerci synthesis, Bollmann-Rauch synthesis, Chichibabin pyridine synthesis, Gattermann-Skitta synthesis, Simatian-Denstadt rearrangement. So these are all the various methods by which pyridines can be synthesized we have studied. And we have also studied about various reactions of pyridines. So we studied about the Menstrukin reaction where the quaternary ammonium salt is formed. We also studied about electrophilic and nucleophilic reactions. So how the nitration, sulfonation and halogenation reactions can occur on pyridine we have seen. We have also studied about oscillation, reactions with organometallics, and free radical reactions and cyclization reactions we have seen. With that, we conclude this particular session on pyridines. Thank you.